Hello, my name is Michael Stewart with Fluke Thermography. Today we're going to use thermal imaging to inspect a common electrical motor for issues that might be impacting energy usage. So we've done a little bit of prep work. We'll show you what we've done when we get over there, but the first thing you always need to have is proper equipment. Make sure you have a thermal imager, it's powered up, ready to go. Make sure you have proper personal protective equipment. Here we have an electrical motor coupled to a pump. The work that we've done in advance, obviously you can see that we've removed the shroud over the coupling and we've removed the cover over the junction box or the termination box. You need to have direct line of sight with thermal imaging in order to do a proper inspection. The first thing that I generally like to do is I'll take a look at the overall motor, the housing itself, and I'll be looking for unusual hot spots or localized hot spots that I wouldn't expect. In a normally operating motor, you would expect nice even heating and distribution across the entire housing of the motor. If you see anything that's off, that could be indicative of a problem. Likewise, if we look at this motor and it's running a lot hotter altogether over the entire motor housing, that's an issue as well. So let's take a look first and see what we find out. Looks quite even, I don't see any issues there. You know, obviously, if this motor were running hotter than usual, that could be an indication that perhaps the cooling fan's not working properly. It's not aspirating properly. I think everything's working okay here. Number one, because the temperature is good. Number two, the fan is operating. If I do find a localized hot spot, that could be indicative of a problem with one of the phases. Maybe some of the windings are burning out. Too much heat will destroy that insulation. Could also be an issue with transients on the line, could be a problem with harmonics on the line causing unusual heating. Either one of these situations, the overall overheating or the localized overheating, can cause that motor to work a little bit harder than it needs to. It will draw more current in order to compensate for the problems that it has, and that will impact your bottom line and your energy usage. Next thing that I'll move on to is the electrical itself here in the termination box. I'll look for high resistance connections. So I'm not seeing anything here, but if I were to see a high resistance connection, it could be too loose, too tight, strands broken on the line, something like that. That will dissipate some of the electrical energy you want to actually make the motor work, and it will dissipate it as heat, as waste heat. And it might not be a whole lot every year, but those kind of connections add up, so definitely take a look at those. I'm also looking to see if there's any overload situation on any of the lines. I'm not seeing anything there. You know, a single phasing motor may be operational and may be working, but you're going to see two of the phases significantly warmer than the one that was shut out, okay? It'll be a lot cooler, and that motor will start overheating. It will actually draw more power just to try to keep running. So definitely look out for things like that. No issues there. I'm going to come up here now and we're going to take a look at the mechanical portion of the motor, the bearings. So once again, we're looking at the shaft end of the motor, and I don't see any issues. If I were to see an issue here with this particular bearing, it would be warmer than the rest of the housing. Usually if something is 5 to 10 degrees centigrade above the temperature of the main part of the housing and it's on a bearing area, something's going on with that bearing. You need to do some extra work to try to figure out what's happening, because a misalignment, a bearing that's just wearing out, over lubrication, under lubrication, all of these things can also cause that motor and this motor pump assembly to operate inefficiently, draw more power, and not actually get the work done that you want it to do. So everything looks fine there, not seeing any issues. All right, you have to be a little bit careful when you're taking a look at couplings and shafts and things like that, because they tend to be a shinier metal, a lower emissivity material. So sometimes you can get reflections off of them that aren't really there and aren't indicative of the actual heat. In this case, I'm not seeing too much going on. I see a little bit of extra heating around, you know, on the motor side of the coupling, but that could be an emissivity issue. I don't really know at this point. I'm not seeing anything significant, and because I'm not seeing any excessive heating on the bearing of the motor itself, tells me that more than likely the alignment's probably pretty good on here. So we're now going to take a look at the pump side and the pump. Don't see any issues here. I think this is operating really well. Any of these problems that I've discussed before is a great opportunity to say, okay, well, what do I do next? I've discovered something that may be draining energy, draining money out of my budget. How do we fix it? Well, you have to be able to diagnose it. So a lot of things, if you're finding a problem with a thermal imager and it looks like it's a bearing related or coupling related, you can then use a vibration tester. From an electrical standpoint, you find a high resistance connection or something looks like it might be overloaded, you can use a clamp meter. If you're finding problems that are localized hotspots, might be a problem with internal windings, it's a good opportunity to use the power quality meter. It could be, as I said, transients, harmonics, anything like that. All of these tools work together in conjunction to help you better maintain your equipment and save energy over the long run. I hope this was helpful to you. As you can see, it's not rocket science. Anybody can do this. You can start saving money and frustration today.